Okay, so the purpose of this recording is to record some of my thoughts that I've learned about rendering audio waveforms. Okay, so in the analog world, the way that an audio waveform works is that it's basically a wave that looks like this. It's represented as a wave, and what happens is that this wave is represented as like an electrical signal that is fed to your speaker driver. So I'm not sure if I can draw it correctly. Looks kind of like this, and there's some kind of material here, and basically I don't really understand the mechanics of it, to be honest, but like electricity goes in and then it causes this thing here to vibrate about like thousands of times a second. And basically those vibrations, when they meet our ears, is interpreted as sound. Alright, so in the real world, the quality of the sine wave could be like really, really high. The quality can be really, really high. So let's say that is like 1 million vibrations a second or something like that. A second. I actually don't even know if that's true, but uh, yeah, let's just assume that it is. So it's like 1 million vibrations per second. It's like really high, but our ears can only, I think, sense like 20,000 vibrations a second, or like that's the range in which it can actually interpret the sound. But when we move to the digital world, so in the digital world, we can't really represent audio waveforms as like a pure electrical signal, because in the digital world, we only have like ones and zeros, and we have to decide on like what frequency we want to represent it. So usually what happens is that in the digital world, instead of having a pure wave like this, what we do is we implement it using points. So it would be something like this, as points. So these points are interpreted as audio, as electrical signals, and then sent into our speakers, which causes the vibration. So notice one thing. Notice that in the digital world, it is of much lower quality than of the analog world, but our ears can't really tell the difference anyways, because you can only hear up to like 20,000 hertz per second. So in the digital world, usually it represents the audio signals as like 44.1 kilohertz per second. So in every second, there would be 44,100 of these little points. And the way that is represented is that the positive side would be a number. So like if we were talking about representing the samples, so yeah, these points here are called samples. As a short, it'll be like 16 bits or 2 bytes. So we would represent this as like 32k, and then this would be like negative 32k. So this is like 2 to the power 15 minus 1. Oh, actually the minus 1 should be up. Wait. Yeah, 2 to the power of 15, and this is like 2 to the power of 15 minus 1 here, like this. Okay, so basically we represent these samples as shorts between 32k to negative 32k. And it doesn't have to just be short. So sometimes it could be like 24 bits or 32 bits. So I believe this setting here is called the bit def. All right. And the most common one is 16 bits. Because notice if you decide to represent it as 24 or 32, it increases your file size by quite a bit, because instead of using 2 bytes to represent each sample, you would have to use 3 bytes or 4 bytes, and multiply that by the number of samples per second by the duration of the audio file. It can be quite significant in terms of the file size. So I think that is why usually we use 16 bits. Okay, so now that we know how how audio waveforms are represented in the digital world, how exactly do we render it? So if we were to actually render this all 44,000 samples per second, it just wouldn't be, it just wouldn't make sense, right? So imagine you're trying to render the waveform, and your screen size could be like 1920 by 1080. So really you only have this many pixels to draw the waveform, and if you try to draw 44k samples in like one portion of the waveform, it just wouldn't really make sense, right? Because you're in reality you can only see so much. Okay, so instead what we do is we downsample this digital waveform. So what we do is we bucketize the original audio sample. So instead of having 44k samples per second, instead we would downsample it so that for each second there would only be like 128 or like 256 buckets. Or you can actually even call this actually I'm just going to use buckets. 256. So by doing that, it is just easier to render this out, and we don't have to use so much processing power to render, because if we use the 44k samples, that would just kill the GPU, and it would be for very little benefit, because recall we only have a limited number of pixels anyways to draw the waveform. So yeah, we would bucketize the original audio sample in buckets, and so it would be, so like say this is like 1 second, and say there's only like 4 buckets, then what we would do is actually not, okay, I just do this, I'll redraw it like this. Okay, so then say this is like 1 second here, then each of these samples here would be like one bucket, or like one down sampled sample, if that makes sense. And there are multiple ways of doing it. So what you can do is that uh, you can take the um, average sample. Yeah, calculate the average samples per bucket. You can get the minimum and maximum samples for each bucket. You can also do like a positive average, negative average, per bucket. And usually, yeah, you can use like all of these stats and information in order to render your waveform. And I think for some different audio software, it might do some more complex stuff, like it might do some interpolation. But yeah, for my implementation, I just focus on mainly these three things here. So now I'll go ahead and show you all what I did. Okay, so in Corgi, what I did was I processed the audio waveforms, and then I bucketized it based on a bunch of different factors, and then I rendered each one just to see what it would look like. So, for example, for one way to render it is just by using the average. So this is the average buckets. Another way to render would be by using the average to decide on whether to use the minimum or the maximum. So, for example, if the average was positive, you would use the maximum. If it was negative, you would use the minimum. Doing the same thing, but instead of using the minimum and maximum, you use the positive average or the negative average. Another way you could do it is by comparing the absolute values of both the minimum and maximum, then choosing the one with the highest absolute value. And then the other one that I tried was comparing between the absolute value of the positive averages and negative averages and choosing the one with the highest. Okay, so this one is using the averages of the positive and the negative side. Okay, so I'll go ahead and render it. I'll just go ahead and run this and show you all what it looks like. Okay, so that's quite loud. Let's go ahead and... Okay, so here are some examples of what the audio waveform looks like after... oh, I zoomed in too much and now it disappeared. Let me just... Uh-oh. Okay. Alright, so first off, let's talk about the average. So in the average case, notice that the waveforms aren't really that great. And the reason is because when you calculate the average per bucket, the peaks basically start canceling each other out, right? So we have the positive peaks and the negative peaks. And these both cancel each other out when you're calculating the average, so it causes it to be not that great of an audio waveform, as you can see here. My favorite one is using the average to decide whether to use the positive average or the negative average when rendering the waveforms. I find that this is much more closer to what you would expect it to look like. So this one here. For this top one, it was using the average to choose the minimum or the maximum. I'm not really a fan of this one. I feel like it causes the the noise for the lower sounds to be much larger than they actually are. And these ones also suffer from the same issue. So this one was using the minimum and maximum. This one is okay. But yeah, my personal favorite is the second one here. So using the average to decide on whether or not to use the positive or the negative average. Okay, I think this one was using the maximum. I'm not really a fan of this one because if you zoom in further, then it doesn't really follow the sine waveform that you would expect. And it just disappeared again because Corgi has a bug where if you zoom in too much, then it just causes the whole entire thing to disappear. And I should file a bug for that. So yeah, those were some lessons I learned about rendering audio waveforms. Alright, I think that's it for me. Hopefully this helps to those who were interested. If not, this will at least help me if I forget about all of this stuff. Alright, have a good one. Bye.